So we've done a lot in this section already on video, and I mean a lot. Like I feel like I filmed 3 hours on this or something, but it's probably only been like 2.5. You know, who's counting? So we're gonna talk about physical properties, interactive forces, and we're gonna kind of tie together some seemingly disparate ideas here. We're gonna bring the whole thing. We're gonna fold it in. You know, we're putting the top on the pie now. We're gonna throw it in the oven. So we've chopped up all the apples. We've put enough sugar in there to give 3 metropolitan areas some solid level of diabetes, and some cinnamon, all that stuff. We've made the dough. Now let's finish let's finish this off, right? Let's take it home. So first off, I'm going to introduce physical properties, but as I'm going to point out when I get there, when I start asking questions about them, I'm really just dressing up like what has more or less attractive forces. Okay, so there's going to be 2 key physical properties we're going to talk about. So the first one is melting point. And you might have a good idea of what this is already, right? This is just the temperature something melts at. Something goes from a solid to a liquid. If you keep it below that temperature, it stays solid. If you go above that temperature, it's going to turn into a liquid. Now, the interesting thing about melting point is, like, when you throw a piece of ice in a drink, that ice stays 0 degrees Celsius. That's the melting point until it's all melted, and then the water starts to heat up. So it keeps things at 0 degrees. If you don't believe me, you can make a thing of ice water, stir it around. You got to get the ice in there first. It's got to get the water cooled down, and that solution will sit at 0 degrees. You put a thermometer in it, and it will stay there as long as you keep stirring it well until all the ice is melted, and then the whole solution temperature will start to rise. And so melting point is the temperature where a solid becomes a liquid. Now, what's the difference between melting point and freezing point? I once blew an entire class away by bringing this point up. Or I didn't bring it up, I just started asking questions, and I might use the 2 terms interchangeably. So what is the difference between melting point and freezing point? Well, it's the exact same temperature. You freeze water into ice at 0 degrees Celsius, and you melt ice into water at 0 degrees Celsius. It's just a matter of, are we bringing it colder than 0, or are we bringing it above 0? So freezing or melting, we're just going one direction or the other over the exact same temperature. So freezing point would be, oh, it's a liquid going to a solid. Well, it still occurs at the exact same temperature. It doesn't matter whether we're going forward or backward. The transition is at 0 degrees Celsius for water. So just a heads up on that. Now, boiling point is the other physical property we're going to talk about. Okay, so we got melting point, boiling point. Boiling point's a little trickier because melting isn't going to occur unless you are on the other side of the melting point. The boiling point is a little different. So evaporation is occurring. So this is going to be liquid going to gas. But that can occur below the boiling point. What the boiling point is the maximum temperature that the liquid can reach during evaporation. So you can have a container of water, like let's say you take a dish of water, and then you put it on the windowsill this time of year. That water is going to evaporate. The sun's going to heat it, it's going to evaporate. The sun isn't going to heat it to 100 degrees Celsius, which is the boiling point. Now, if you take water and you put it on a stove, and you turn the stove on, you're going to heat that water up. You might start to see some steam or whatever, and it starts bubbling. And so when you're bubbling, that's boiling. That's the boiling point. That water will not go over 100 degrees Celsius. That's the maximum temperature it can reach. You can turn the heat up on your stove. Guess what happens? It doesn't get hotter. It just boils faster. It might even boil over. And that's because what happens is the rate of evaporation increases to offset the increase in heat being put in, and so the temperature stays the same. So it's the maximum temperature you can reach. Now, boiling point and melting point, those can shift at different pressures, And so for melting point, you don't see a huge shift. It's not super important unless you're really dealing with some like high-end scientific or medical equipment. But boiling point, just by being at elevation, you have less atmospheric pressure. So we get atmospheric pressure because there's all this air pushing down on us. Gravity's pulling all this air on us. Well, if you go to elevation, there's less air pushing down on you. You get less atmospheric pressure. And so if you look at cooking directions on something like macaroni and cheese or whatever, anything where you got to boil water and cook something in boiling water, the directions will be different if you're over, I don't know what it is, 2,000 or 3,000 feet or something. Baking directions, instructions change at different elevations. I would go hiking with my dad. He worked in Yosemite National Park, and we would hike. And so they're already, I think the valley floor, if I remember right, was around 2,000 or 3,000 feet. And then you'd scale the side of the valley, we'd go hike up. And so you'd end up around, like 4,000 feet or so. About at least 1,000 feet more than you were at the valley floor. So, somewhere around 3,000 to 4,000 feet. And I remember he got this chili, this like instant chili, called Cha-Cha Chili. That was the name. And it was breakfast one morning. Because that's what you do. You're backpacking. You don't want to carry anything heavy. So pancakes were off the menu. And I was like, oh, I'll have this Cha-Cha Chili. It's like this instant chili. So you just boil water, you pour it in a cup. You ever had like an instant soup cup? You put the lid back on, and you hold it down, and you wait. Well, we were at elevation, so the water didn't boil at a high enough temperature. The water wasn't hot enough to like really get the chili put together right. And so I ate like this lukewarm, crunchy chili for breakfast. I still despise Cha-Cha Chili to this day. There was a bear that came through our campsite the night before. I could barely sleep. And we were just sleeping out. Like, we didn't have tents. We were just in sleeping bags. But we had the bear box. You have to get a bear box when you go to Yosemite, by the way. You take the bear box, you throw all your food in the bear box, you throw it over there. And they only have black bears, so it wasn't like I was at risk. So it was just like the world's largest raccoon stomping around a few feet from where I was sleeping. But still a little nerve-wracking. But anyway, that boiling point was lower because we were at elevation. So it can shift with, pressure changes. But what it is, again, is the maximum temperature that a liquid can reach during evaporation. So evaporation can occur, and does occur, at lower temperatures, right? Water's evaporating out of a dish you have on the windowsill. It's not boiling hot. Like, you can put your finger in it and you don't get burned. Whereas if you did that with the stuff on the stove that's boiling, you would get burned. You'd have a boiled finger. So this is the maximum temperature, but it's not the temperature that evaporation occurs at. Whereas this is the temperature that melting occurs at. And so we're saying, this is liquid to gas. Okay? So, as attractive forces increase, so if we have an increase in attractive forces, this is going to be an increase in our melting point or our boiling point. Whichever one we're talking about, they behave the exact same way. So, more attractive forces, higher melting point, higher boiling point. So, the stronger the attractive forces are, the more it's going to try to stay like a solid. And so when you melt a solid, you're essentially breaking up the structure. You are making the molecules interact with each other less. You're overcoming the strength of those interactions. So they're starting to kind of, you kind of get liquid. And then when it comes time to boil, you've got to pop that molecule completely away from its neighbors. You've got to push it out into the cold abyss, away from its friends. And so the stronger that attraction is, the more you've got to push that molecule. And how do you push that molecule? By getting it hot. And so it starts moving around faster and faster, and it pops off. So that's what you do. And the stronger those attractive forces are, the more you've got to push that thing into the gas phase. The more you've got to heat it up, the higher the boiling point is going to be. higher the melting point's going to be. So just remember, more attractive forces, larger melting point, larger boiling point. So that means I could ask questions like, you know, which of the following has a higher boiling point? And then I can show you some molecules. Okay. And, you know, we'll go boom, 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 boom. Give you 3 options here. You know, which of those has the highest boiling point? Well, what am I asking here? I'm dressing this question up, but it's a question I've asked before, not necessarily with these 3 molecules. Kind of looks like the old, like, you know, ape becoming a human being, you know, drawing. This is like the Neanderthal with the club, and then, oh, look, there's the guy on their iPhone, right? So, which of these has the highest boiling point? What am I really asking? Like, let's peel back the layers on this onion a little bit. I'm asking, which of these 3 molecules that I've drawn has the strongest attractive forces? And you know how to answer this question already. This is what I'm asking. Which of these has the strongest attractive forces? Well, what's this got? What's the strongest attractive force this thing has? It's all nonpolar, so it's got dispersion forces. What's this got? What do we got here? What's this? Well, we got a polar bond. This is a Cl, so it doesn't hydrogen bond. Okay, so this is a dipole-dipole. So this is stronger. Middle's winning so far. What do we got over here? Well, we got all molecules about the same size, but this one has hydrogen bonding, which is stronger than dispersion. And it is also stronger than dipole-dipole. That's our winner. That has the strongest attractive forces. That's going to have the highest boiling point. I can also flip this on its head a little bit. I can say, well, what has the lowest boiling point? Which has the lowest boiling point? I'm going to be lazy. I'm not even going to draw more molecules. So which of these 3 has the lowest boiling point? Well, again, let's peel back the onion before I answer it. What am I asking here? Well, I'm asking for the weakest attractive forces. Which is the one with dispersion. Okay? So, do another example here, you know. Which has highest melting point? Well, I gotta draw some molecules, so don't panic. Like, you're not there yet. All right, let's say we have okay. Which of these has the highest melting point? I might have razzled and dazzled you here a little bit, a little showmanship. So again, what I'm asking for is strongest attractive forces. Okay. Higher melting point means higher attractive forces. And then it's a question you know how to answer. So which has the strongest attractive forces? Well, oh, this thing can hydrogen bond over here, can hydrogen bond over here. This one's got dipole, 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 dipole. It looks like it's a tie, right? Or does this one have greater dispersion forces to take it home? So I drew carboxyl groups. You know, it's the old magician's trick. I get you to look over here, and then I pick your pocket over there, right? Maybe you fell for it, maybe you didn't. Either way, I already know your brother's maiden name and have opened 4 different credit cards. Alright. And I will use them to just buy whatever I want. You can't stop me. Maybe I'll send you something if I feel like it, because I have your address now. Alright, so which of these has the strongest attractive forces? Well, it's a tie until you realize that dispersion forces, this has a larger surface area, pushes this one over the edge. dispersion forces can act as a tiebreaker. In the event of a tie, in terms of everything else, long chain wins. That's what we look at here. Alright, so this has a lower melting point, this is a higher melting point, because this has more attractive forces, this has less attractive forces than its neighbor there. That's what we're looking at. And yeah, that pretty much, I think, ties it all together. So now, just for fun, these are not numbers you have to know, but I always like to use them as kind of an example. Alright, so if we look at like the boiling point or melting point of different compounds, so like if we look at like NaCl versus MgS, this has more attractive forces. It's going to have a higher melting point, and its melting point is about 2000 degrees Celsius, whereas sodium chloride is 801 degrees Celsius. So these are very high melting points. Okay? It's not easy to melt a salt. You know, if you want to, get some salt, pour it on a pan, and then set your oven for 801 degrees Celsius, which is roughly, you know, about 1650 or so, you know, about 1600 degrees Fahrenheit. So just crank the oven to 1600, very roughly. You can do the exact conversion if you want. And you can melt some salt. You can make some magma. Now it's going to melt your pan first, but that's not a big deal. You know, just get some magnesium sulfide and make a pan out of that, and then you can melt the sodium chloride. But remember, this has more attractive forces because it is a +2 and a -2 ion versus this being a +1, oops, and a -1. So you would expect this to have a lower melting point and this to have a higher melting point, and it does. And this is not a negative, by the way. This is approximately, give or take a few degrees here or there. Maybe it's 1999 or something. Another example, if we compare, say, water versus ammonia versus methane. These are all going to be well below our ionic compounds, and I'm actually going to show you the boiling points for these. So, water, 100 degrees Celsius. Hopefully you knew that, right? Our Celsius system is built off of the freezing point being 0 and the boiling point being 100. So water literally defines the scale. Ammonia is -28.01 degrees Celsius. So it was actually one of the first refrigerants ever used. That'll get your ice cream nice and firm right there. And it's nice that it was non-flammable, which is a big deal. You can use propane as a refrigerant, but then it can explode, which is a drawback in your house. The smell is horrific, so you know when it's leaking, that's a plus and a minus all in one. But the issue was that if it got a leak, ammonia was denser than air, and it would settle down. And so the early refrigerators, if someone had a large refrigerant leak at night, and they weren't sleeping high enough up off the ground, they would asphyxiate and die. That was one of the issues. Now, it is still used as a refrigerant today, so it's very affordable and environmentally friendly compared to the old chlorofluorocarbons that put holes in the ozone. In fact, I live over by I literally live by an ice cream factory here in Eugene right now for a few more weeks before I move. And they actually use ammonia. They have giant ammonia tanks. I walked by and saw them one day when their gate was open. So they use ammonia still for their giant factory refrigeration system. Like, they're literally making tons of ice cream every week, and they're using ammonia to keep it cold. And so, you have a system that lets the ammonia evaporate, and then you compress it back down into a liquid and evaporate it. And so you can create a room with that temperature. Now, methane, also known as natural gas. Just think for a second. So first off, this is the difference between OHs and NHs. This has a much higher boiling point, so it has stronger attractive forces. Do you expect this CH4 to be, where do you expect it to be compared to these two? Just take a second. Think about the attractive forces here. And then, would you expect it to be less than this, more than this? Is it less than this, more than this? Somewhere between the two, or is it down here, or is it above? What's going on? So, this is an example of the difference just between this type of hydrogen bonding. Does this hydrogen bond? No. Does it have any polar bonds? No. So that means it's a non-polar molecule. And it doesn't have a ton of surface area. It's a pretty small molecule. And so it turns out that its boiling point is negative 161.5 degrees Celsius. So these are all boiling points, just to be clear. So not quite apples to apples here, but apples to oranges. So it's very low. So that will definitely firm up your ice cream. Now it is, typically used for, heating and cooking and things like that, because generally we burn it. We don't just like cycle it through. You'd have to make sure you had a 0 spark set up to do that. I do not recommend using this as a refrigerant at all, but it could theoretically be done. Get you nice and cold. You just have to worry about blowing up. Alright, so let's see. I guess if we want to compare them, I do have the boiling point for sodium chloride here, because why not? So it is 1,413 degrees Celsius for a boiling point. So ion-ion attraction, very strong in comparison. And again, you do not have to memorize these numbers. I just like to use them for demonstration purposes. You can see the effect of increasing attractive forces. This has stronger attractive forces. Like, it is locked in. Good luck boiling salt. This, okay, yeah, like, we can do that. This, you have to like put effort into keeping it from boiling. And this, I've never seen liquid methane. Okay, I'll be honest, I've worked with some stuff in my day. I've never seen liquid methane. Could you get it? Yeah, but we probably wouldn't do it by this trick. We would probably do it by compressing it into a cylinder a lot. Would be the easiest way to get it, not by getting something that cold. You could do it. I mean, liquid helium, it exists, and it's used for cooling magnets and things like MRIs. The older ones, I think newer ones actually have better magnets now, so they can use like liquid nitrogen or something. But yeah, so getting really cold temperatures, we can do that by evaporating really small nonpolar molecules. That's what we do. And like modern refrigerants are actually just kind of, they're like designer molecules that we kind of tailor make the evaporation point, and we do things like make sure they're not flammable. And then we had to make sure they didn't put holes in the ozone. So the old R12, the old Freon, the world came together. I think it was in Montreal. They signed the accord or the treaty or whatever it was, or agreement, that everyone would phase out Freon because it was putting holes in the ozone. And last thing you want to do is make the Australians angry by opening up the skies above them, as well as Antarctica. But no one was repping them. Like, the penguins didn't even show up to the meeting, so it almost didn't pass, but then it did. And we've actually had the hole in the ozone closing back up because we stopped using those style of refrigerants. But they had to make new ones. And so now they have like R401 or something like that for cars. Or, I think it's R401 or R411, something like that. And that doesn't put a hole in the ozone. So first off, they try to capture it. They try not to lose any when someone's servicing equipment. But leaks happen. It escapes. But when it does, it's not as bad. So it doesn't start eating a hole in the ozone. So you never quite know the properties of your molecules till they get out there sometimes. And it was totally inert. Freon was totally inert. It was totally safe. The only thing you had to worry about was making sure you had air to breathe when you're around it, because it could still fill a room with Freon. We can't breathe it, we die. Like, we need oxygen. But otherwise, it's totally non-flammable, completely inert. There'd be no side chemistry going on. It wasn't going to corrode your equipment. Like, it was great. It was perfect. And if it did get out, it would just go all the way. It would just go into the atmosphere. You didn't have to worry about it. Well, it turned out that when it left the ground and it went into like the atmosphere, it would hit a certain level and it would start reacting with solar rays and other compounds up there, and it started a chain reaction where it started chewing up ozone. Tons of molecules of ozone. There's really no way to if you weren't looking for it, you wouldn't expect that. But once we saw it happening, once we figured out what happened, we adjusted. And so, our decisions can have a huge effect. I mean, that was a very important protective layer in terms of absorbing UV radiation and keeping it from getting to the Earth. So if you ever go to Australia, my mother-in-law is living over there now. She's, I guess you could say she's Australian, but she grew up in the United States, and she moved over there after having like kids and stuff here, like later in life. And if you ever go over there, everyone, if they go to the beach, it's like the 1920s. Like they are covered. Like they wear a shirt. You know, they don't have any skin exposed, and what they do have exposed, they have sunscreen all over. And a lot of that was because one of the holes in the ozone that developed just happened to develop right over Australia. Because if there's ever a corner of the Earth that is hated by any sort of higher power, it is Australia, because they have the most poisonous snakes. They have crocodiles, because why not? They have incredibly poisonous jellyfish. There's a plant that if you touch it, it will hurt so bad that most people kill themselves because the pain just doesn't go away. And then also, my mother-in-law lives there. No, I'm just kidding. All right, because that's on the internet. She might see something. All right, anyway. All the most dangerous things are there. And then on top of it all, boom, increased rates of skin cancer. Because more UV radiation is getting there, more skin damage, more cancer. So, it's a beautiful place. Don't get me wrong. Just if you ever pick up a rock or anything like that out in the countryside, you know, be ready to throw it at a snake. That's what they do. Like, you should shake out your boots, you know, whole rigmarole. Alright, so we'll close this section out now that I've done my series of Australia jokes, and which were definitely in my notes. I don't just do that off the top of the head. And so we've got these two physical properties. We've got boiling point, we've got melting point, and really what we're doing is just looking at attractive forces. You got those 4 attractive forces, each stronger than the next, and then we can rank within them. And so this is just a way of demonstrating those effects. Do not memorize these numbers. I mean, that one you should just know, but don't worry about like, oh, what's the point of methane, whatever. Okay, so this is going to be a key topic that carries in the next one in terms of attractive forces, because this is what drives molecules interacting with each other. So when you get something to dissolve and you make a solution, what we're going to do is jump from, right now we're talking about like, oh, I have a container of one type of molecule. How are they interacting with each other? In the next section, it's going to be like, I have a container of one type of molecule, and then I sprinkle some other type of molecule in and stir it around. How do they interact with each other? So now we're taking it to the next step. So instead of having multiple of the same molecule, we're going to start making mixtures and talking about what happens. Do they, blend into each other? Do they separate from each other? That's what we're going to talk about next. And attractive forces is so key to all of that. So just be aware.